What's up, guys? My name is Lorenzo. Today we're going over lab 4, the magnetic field of a dipole magnet. Oh, click, click. Okay. So the purpose of this lab was to measure the magnetic field of a bar magnet, analyze the relationship between the magnitude of a magnetic field and the distance away from the magnet, and determine the magnetic moment using the Biot-Savart law. So our results ultimately showed that the dipole moment was 1.55 times 10 to neg 10 to the 8, and then our distance dependence was negative 0.9131. So these are the main physics constants that are used. The Biot-Savart law pretty much calculates the magnetic field of a dipole, depicting the bar magnet as a dipole. And then this equation shows that there. And then the magnitude of a magnetic field to a bar magnet falls with distance as shown by that. And then we can plot the following equation to determine the experimental value of n, the distance dependence, by plotting the following values, which is would be the natural log of the magnetic field versus the natural log of the distance. And then eventually the natural log of k, which is the constant, can be useful to help find the magnetic moment, mu. Uh-oh. So the system was a bar magnet and everything else was surrounding. First, we aligned our phone with the Earth's magnetic north-south axis by rotating until the X component on the magnetometer app read zero, and then we placed a meter stick directly underneath running east-west, which compensates for the presence of Earth's magnetic field. And then we also placed the phone perpendicular on a stick to find the position on perpendicular where X component is at maximum, and then rotate that 9 degrees, move it along the perpendicular from the max Y component. And then we find the distances from magnet where the x component of magnetic field equals certain values. So this is what the data that we found. The main key observation was that as we place a magnetometer further away from the magnet along the ruler, the magnitude of the magnetic field did decrease, which does make sense. And then this was the graph that, or yeah, the graph that came out where we plotted the natural log of magnetic field versus natural log of the distance. And then we found that the slope was negative 0.9131, which is the distance dependence, and then we found the intercept of natural log of k, which is 3.4328. And then these are the calculations that we use to find, and so we use the Biot-Savart law for on-axis field of a magnetic dipole, and then we plugged in all our values that we calculated to ultimately find the magnetic dipole moment. And then this was a data for part two, where we recorded distances where the net magnetic field is equal to 100 micro, and then we found the perpendicular distance where we found that that was 0.277 meters, and then the net magnetic field was 62, which is does seem a bit high, but we'll figure it out later. And this is pretty much a glow script that I made. First, it calculates the magnetic moment, and then it calculates the magnetic field of that function, and then it also created different observation points along the axis and also perpendicular to the magnet. And these pretty much create the arrows of those observation points. And then we're using the measured perpendicular distance of 0.277 meters. We found the hypotenuse distance, and then we calculated the magnetic field at a 45-degree location. So this is pretty much what our data shows. Here we have the on-axis ones and then the perpendicular ones. And up here is the 45-degree one, which is going to be a bit small, much smaller since it's further away. And then we also have like the vectors and then the calculated magnetic field vector at that 45-degree angle distance. So obviously from the experiment, we found that the magnetic field was quite a bit too big. And then our glow script calculation would be at the 45-degree angle, had a magnitude that's just much smaller. So I think some of the possible sources of error was of other electrical objects near the experiment. And like the phone also could have rotated slightly. So now like the Earth's magnetic field would have influenced the results. So if we hadn't orientated the experiment to compensate for the mag north and instead laid out your meter stick some intermediate angle, I think Earth's magnetic field would influence the results mix because it would mix with the magnet's field, affecting both its magnitude and direction. And then if we were to stick two identical magnets together end to end, these two identical magnets would create a bigger magnet and moment, which would thus increase the magnetic field. That's it.